So 5.4, rational functions. What we are really after when we're talking about the functions part, remember rational means some kind of goofy looking fraction, right? Where the tops and the bottoms sometimes cross out, sometimes they don't. But when we're talking the function part of it, we're thinking graphically. What does this thing look like on a graph? Okay, so let's talk a couple things. Asymptote. What is an asymptote? Well, let's imagine we had a graph here. An asymptote is a line, and it can be a horizontal line and it can be a vertical line, but it's basically something that as a graph decreases, it gets closer and closer and closer to this, but it can never cross it. So that's called an asymptote. So sometimes we have asymptotes that look like vertical lines as well. So that means, and there could be a function on either side, right? Maybe the function's coming this way and then it gets really, really close there. And then maybe then it starts down here and it goes away from. But it can always get close to an asymptote, but can never cross it. So at an asymptote, usually things are undefined at that moment, right? So it's undefined, which is why you don't see the graph cross over that line, right? It's kind of the hold the line type thing. So what we're going to talk about is rational functions and where those asymptotes come in so we can get an idea of where these graphs occur. So let's talk about a vertical asymptote. Vertical meaning the up and down asymptote. So we're trying to find asymptotes that go bing, 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 like this, right? And there could be multiple asymptotes. It could be one over here, one over there, which just means then the graph is kind of contained inside of these. And it could look all kinds of funky shapes, right? We never really know exactly what these graphs look like. But again, asymptotes themselves mean the graph will never cross that point. It will get super duper close, but never cross the point. So vertical asymptotes, this is where a function is undefined. That is called vertical asymptote. That's where those will occur. So let's say that we had, again, like 3x plus 1 on the top, and on the bottom we factored, and we got x plus 2, and we got x minus 8. So where is this function going to be undefined? It's when this group equals 0 or this group equals 0. So we'd say when x equals negative 2 and when x equals positive 8. Those would be vertical asymptotes. So if I had a graph, I could literally go to x equals negative 2. We're going to put a little dashed line, and we know that the graph will never cross that. 1, 2, 3, 4, 5, 6, 7, 8. And then I can put another dotted line at positive 8, and we know the graph. Now, I don't know what the graph is doing in between. That's a whole different set. Usually when you have two asymptotes, you have one that looks like a U shape. It kind of looks like that a lot of times. But vertical asymptotes are when the function is undefined. So it's those bad x values that would cause problems. That would give you vertical asymptotes. All right? So that would be vertical asymptotes. Let's talk about horizontal asymptotes. Horizontal asymptotes. Now, if I did like this, horizontal asymptotes would be going the other way. Now, it could just be one horizontal asymptote. It could be multiple horizontal asymptotes. Or maybe there are no horizontal. Same with vertical. There might be no vertical asymptotes. But we just need to know. Okay, so let's think about a function. And again, let's do just any kind of function. Let's say it's 3x cubed minus x plus 5. Let's say we had like a 2x squared plus 1, something like that. Okay, so horizontal asymptotes are all based on degrees. Degree at the top versus degree on the bottom. If the degree on the top is greater than the degree on the bottom, we'd have no horizontal asymptote. Okay? So if the degree top is greater than degree bottom, then we have no horizontal asymptote. Okay? So that's going to be one function that we want to say. If it's the other way, let's say it's 3x squared minus x plus 5 over 2x cubed plus 1. if the degree on the bottom is greater than the degree on the top, the horizontal asymptote is y equals 0. It's literally right down the middle of the graph. Okay, so then what is the last one? It is 3x squared minus x plus 5 over 2x squared plus 1. If the degree on the top is the same as the degree on the bottom, then your horizontal asymptote is the coefficient on the top divided by the coefficient on the bottom. So y would equal 3/2. Right? So there it is. So it's going to be which scenario holds true, right? So is the degree, and the degree is the biggest value that we see. Right? So that's how we're going to find horizontal asymptotes. Lastly, what is a zero of the function? A zero of the function is where where y equals 0. Where y equals 0 or where x equals 0. Typically, when you hear about zeros of a function, it's when y equals 0. So if I gave you a function, y equals x plus 2 over 3x, we would literally want to plug a 0 in for y, and we would solve for x to figure out what value of x would give us 0, right? And something would have to. But what is that something? That means, literally on the top, make the top equal to 0. And whatever the top equal to 0 is going to give you a 0 on the function, because 0 divided by anything is 0. So we don't even have to do all this mess. We just cut to the chase. X plus 2 equals 0. So when x equals -2, we would have a 0 of the function. Now there might be multiple zeros, because it could be a quadratic equation, but we'd have to do and see. All right, so that's what it looks like. Let's do some problems. Identify the zeros and vertical asymptotes, okay? Zero and vertical asymptotes. So the first thing, in order to find zeros, right, we are going to take the top, x squared minus x minus 12, set it equal to 0, and go. Okay, so here we go. We got to, in order to solve, we're going to have to factor two things multiplied 12, add to a -1. It's going to be x minus 4, x plus 3. So x is equal to 4, and x is equal to -3. There are my zeros, or when those values occur. That's where they would occur on the graph of that. Okay, now let's talk about vertical asymptotes. Vertical asymptotes are when the bottom equals 0. Whoop, done. We got a vert asymptote. What if I do that? Vert asymptote. Okay, and then it does say graph. We're not going to do the full-on graph. I want you to know the different logistics. So there is a 0 at 1, 2, 3, 4. So we'd put a big old dot at 4. Where x is 1 to -3, we'd put a big old dot. And then right where x is equal to 0, we're going to have a vertical asymptote. Okay, what does that mean, though, about my graph? Well, we don't know if it's shooting up or shooting down, but we might have a graph that's curving this way, getting close to that asymptote, and then curving away. And then this side might do something like this, right? I don't know exactly what the graph looks like, but I know where the zeros are, and I know where the asymptote is. That's what we're after right now, okay? Number 9, let's try it. All right, let's find the zeros and the vertical asymptotes. So first of all, let's find zeros. So it's x squared minus 5x equals 0. So when the top equals 0, so let's factor out an x minus 5 equals 0. So it looks like when x is equal to 0 and when x is equal to 5. Those are my zeros, okay? Let's find vertical asymptotes, right? Remember, vertical asymptotes are when this thing becomes defined. It's only going to become defined when the bottom equals 0, so when x equals 2. Got it, vertical asymptotes, okay? And then yes, we could graph and we could keep going. We can add a table if we wanted to. All right, zeros, here we go, quickly, zeros. It's going to be when x squared equals 0. I'm going to square root this side. I'm going to square root this side. X is equal to positive or negative 0. We know there's no such thing. It is literally, there's only one 0. It's 0. Where's the vertical asymptote? It's when the bottom equals 0. Looks like when x equals 1. Okay, there we go. All right, identify zeros and asymptotes of each question. Okay, let's take it a step further. Let's find, okay, first of all, zeros. What are the zeros? It's when the top is equal to 0. So when x squared plus 3x plus 2 equals 0, that looks factorable. So let's go x plus 2, x plus 1 equals 0. How about when x is negative 2, when x is negative 1? There's my zeros. All right, let's think vertical asymptotes. So let's go vertical asymptotes. When do we have vertical asymptotes? When the bottom is equal to 0. 3 minus x is equal to 0. Let's subtract 3 from both sides. Negative 3 equals negative. Negative x equals negative 3. X equals 3. So there's a vertical asymptote at 3. How about we throw a horizontal asymptote on there? Horizontal asymptote. What is the horizontal asymptote? Okay, here we go. Top degree is 2, bottom degree is 1. Top degree is bigger than bottom degree. No horizontal asymptote. It's kind of a funny word, asymptote. It's the P in there that's kind of, you don't hear. Okay, should we try it again? Okay, so let's do this one. Find the zeros in the function. Here we go, zeros. That's when the top is equal to 0. Oh, when x is equal to 2. Perfect. Let's go vertical asymptote. That's when it's undefined. So when the bottom equals 0. So I'm going to get x plus 6 equals 0. So it looks like when x is 0, that's going to be a vertical asymptote. But there's also going to be one at negative 6. 2 vertical asymptotes. How about the horizontal asymptote? Horizontal asymptote. Okay, here we go. Degree on the top is smaller than the degree on the bottom. Top is smaller than the degree on the bottom. It's an automatic y equals 0. That's my horizontal asymptote. All right, good. All right, let's move on to the next one. Next little section here. And then I don't think we're going to do the last part right now. I think we'll talk about that later. Identify holes in the graph. Okay, what's different with holes in the graph? Holes in the graph mean that originally there would have been a problem, but we were able to factor out that problem. And so that actually creates a hole in the graph. It's kind of funny. Is that a funny word? But watch, because you're going to see, because then the function usually becomes linear. So let's check this out. Why don't we rewrite the function as its factored form? Okay, so let's take the top and let's factor it. How about we go x minus 3, x minus 2. On the bottom we go x minus 3 and x minus 1. Okay, how about we do that? All right, now if we do that, what happens? This happens, this happens, right? So when that happens right there, then now we have this new function, and it's x minus 2 group on the top, x minus 1 group on the bottom. Okay, so now we can continue to do the things that we were doing, right, in here. So that's going to be like finding all the things, right? So let me think about, is there a 0 of the function? Absolutely, when x equals 2, because that's when the top equals 0. Is there a vertical asymptote? Absolutely, it's when the bottom, x equals 1. There's a vertical asymptote. Is there a horizontal asymptote? Absolutely. It is, let's see, it's 1 and 1, right? So if the degrees are the same, then it's the leading coefficients. Well, they both have a 1, so then it would be y equals 1, okay? But now, is there a hole in the graph? Well, that's a funny thing. A hole, you have to revert back up to here. What did you cancel out? There is a hole at x equals 3. Literally, if you were drawing a graph, well, check out all these things that we could put, right, on this graph. Let's get a graph going here. I should just get a graph. I should just digitally put a graph in here. But let's do this. There's a 0. There's a 0 at x equals 2, so there's a 0 there. There's a vertical asymptote at x equals 1, so that's going to be like that. There's a horizontal asymptote at y equals 1. Okay, that's really limiting where my things are. And then there's a hole at x equals 3, right? So this thing could potentially look something like this, where it goes like this, and then it goes, oh, but we're really, before we get too far, actually, I'll go ahead and graph this. This is probably what the graph looks like, and then probably this one's over here because it would be trapped inside there. That's most likely what it looks like. But where x equals 1, 2, 3. So at this point right here, there is a hole in the graph, literal hole in the graph. So let me actually see if we can't erase that right there. And let's put a hole on it. Yep, there's a hole. Literally, like it looks like the graph and then boop, it gets interrupted and then it keeps going. So this is what a hole is. And a hole comes from, because the original graph right here, once we factored it out, you didn't see it. But before you factored it out, yeah, there was another problem besides just x equals 1, x equals 3 happened. Okay, so let's do the same thing here. Let's find just the hole in the graph. We could find everything, but let's find the hole in the graph. So in order to find the hole, again, here's what you do. You factor. So it looks like we're going to go x minus 2 over x minus 2, right, that group. Okay, what happens? That crosses out. So then I would rewrite this thing as f of x equals x minus 2. Right here, it looks like we have no problems, but a hole is when there was a problem. So when x equals 2, that was a problem before we factored. So it would create a hole in the graph. Right. So that's what we're going to be doing. We're going to be thinking zeros, vertical asymptotes, horizontal asymptotes, holes in the graph. We're not actually going to get around to graphing these things, like legitimately graphing. We're just getting some of the parts of the graph in the right direction.